This last one is the one that I promised is going to be interesting because it's going to help us combine depth estimation, optical flows, and semantic segmentation. And the idea is that you want to increase the robustness of your depth estimator. You want to adopt it better depth estimation. You have a video, you have some pre-trained neural network that are single image depth predictors. And we just saw a couple of examples of them. Some of them were supervised, trained, the other ones were unsupervisedly trained, but they're going to give you some estimates for your depth, and they're going to be not so great. Then the rest of the algorithm is going to do some joint pose estimation and depth deformation from different camera views. There is going to be some geometry aware depth filter. So these ones I'm being a little bit vague at this point, but then it's going to become clear. And then they're going to give you better estimates for your depth. First of all, you have a video. You can look at your video using pairs of frames. The pairs could be one time step different, like what you have here. These are one time step apart. They could be two time steps apart, or they could be four time steps apart, or even further, 8 time steps apart, and so on. And that's going to give you a set of frames that you're going to work with out of your video. Not only you have some initial estimates for your depth, you're going to have an optical flow estimator. This is also a pre-trained algorithm, like the ones that we covered. You know how your pixels are going to change from one frame to the next frame, and according to what arrow, what vector. And these are your optical flows, which are going to map a pixel in frame I to its corresponding location in frame J. That one we're going to use to go from one frame to the next one, or to warp our images from one frame to the next frame. And at the same time, you're going to use them to make sure that sometimes these optical flows or the estimates that you get are not perfect. You can make sure that they are perfect, or keep the pixels that are perfect in your loss function using a mask. Keep only the ones that are consistent. If I go forward according to this optical flow, maybe some of the boundary pixels are going to get messed up. Maybe some of the frames are too far from each other, and then this baby is no longer running in the scene. It's absent altogether. So you just keep the ones that are consistent from one flow to the next one according to your flow. And it's a mask. It's a 0-1 mask. The ones that are 1, you keep. The ones that are 0, you discard. You're going to use a segmentation algorithm. We are going to cover mask or CNN later on. It's for multi-person segmentation. We are going to cover that, or we covered some other segmentation algorithms also. And the job of the segmentation algorithm is also to get rid of the objects in the scene that are moving, like people, animal, vehicle. These classes are likely to move, so you're just going to remove them from your loss function. Again, this is a mask. It's either a 0 or a 1. You keep the pixels that are 1s, you discard the ones that are 0 in your loss function. Now you want to do depth estimation. You have a pixel in 2D. You first turn that pixel into 3D coordinates. How do you do it? You first, let's assume that you know this. Let's assume that you know your per frame scale coefficient. Let's assume you know this. Your depth, it's coming out of a CNN. It's the initial estimates. So you know that. And then your P is in your 2D coordinate, and make it 3D, and then use the depth to make your 2D pixel and turn it into a 3D corresponding coordinate. So here you're using your depth estimator to turn your 2D pixels into 3D pixels or 3D coordinates according to the scale, the depth, and the 2D or adjusted 2D coordinates. What else? Now you go from one frame to the next frame of your video. The camera probably moved while you were filming. It is gonna get translated. It's gonna get rotated. So there is some rotation matrix for camera used for frame I. There's gonna be a rotation matrix for frame J. And there is some intrinsic properties of your camera itself. So now you're converting a 3D pixel or 3D coordinate from frame I to frame J, from this frame to another frame in your video. And as I mentioned, these are rotation matrices. translation matrices or translation vectors, and some intrinsic properties of your cameras. What you can do, let's assume you know your camera. This is an assumption. This is a wrong assumption. Let's assume you know the properties of your camera, the rotation, the translation. Write down a loss function over all of the pixels that are consistent according to your optical flow estimation. Write down a reprojection loss. What do? You have a pixel in frame I. You take it to frame J using this operation. You use your optical flow. This is now P is 2D. You use your optical flow. You're still in 2D. You went from frame I to frame J. Use this CJ function to take you to 3D. Now these two have to match. And then I'm going to tell you what is the symmetric loss that you're going to use. And there is some camera properties that you assume you know. And the depth is coming out of your depth estimation, which you're going to train over. The question is, what are these camera coordinates? We can reverse this loss function. Assume you know your depth and optimize over the camera. So you're going to have this multi-step. Optimize over camera, then optimize over depth. Camera, depth, camera, depth. One step of optimization per each round. But there's going to be a catch. This is not going to be accurate because you only have one scale. You need to relax the scale a little bit so that you have a per pixel scale. And you're going to replace S by a phi function. So now this is a depth deformation model. So don't worry too much about it. All it's doing is you have now multiple scales at multiple locations on a grid. And then you are just deforming that using bilinear interpolation. Why is that? Because this optimization, optimize camera first, then depth, camera, depth, camera, depth, is gonna diverge. And the thing that you need to blame is this S function or the scale, because this process is very sensitive to the scale that you're choosing. If you get your scale wrong, then you're optimizing over the wrong thing in the next iteration. And then from one iteration to the next iteration, you're accumulating error. Okay, this is what you're going to use to train your algorithm. What is going to be the testing? What do you do during testing? You need to know, if I give you a pixel, what is the corresponding depth value? Look at the neighborhood of that pixel, not only in space, but also in time. This is just a neighborhood of that pixel. Use your optical flow. Each one of your pixels, you're going to translate from frame I to frame J. These are in 2D. Make them 3D, and then read off the Z coordinate. So that's what you're doing. You're reading off the Z component of the 3D pixel. And F is your flow estimation. And if two frames are really further apart from each other, maybe two, then you're concatenating those two arrows, those two vectors. You're chaining them together to take you from one frame to perhaps two frames in front of you. And then there is some weighting, and this has to do with what's going to happen on the boundaries. At the same time, try to be consistent. Because if you take a 2D pixel, make it 3D, or if you take a pixel in the neighborhood of P, this is 2D, use your optical flow, go to frame J, and then come back to frame I using this projection matrix, then it has to be consistent. If it's not consistent, penalize it. Don't include that in the prediction. Some good data sets for these are Sintel, Davis, and cell phone video data sets. What I owe you are, what is this loss ratio? This is the exact formula for it. Another thing that I owe you is L special. And where do you use it? You're going to use it in this similarity loss. I think it's a good time for me to stop. Sorry for going 2 minutes over time. Any questions? For those of you who want to leave, you can leave.
Quick question about kind of like every little loss that we're building to make all these moving parts work. Like, I don't know, I just feel like.
Yeah, the reason is for classification, there was only one loss function, cross entropy, and then we were focusing mostly on designing our neural networks. Now we are actually going beyond designing neural networks, because now we are taking that for granted. See, this is a neural network. And now it's about knowing your data, knowing what the task is, and then writing down a good loss function. And it's not always the case that you know your loss function. It's not always the case that you have some supervisory signal. It means that you need to become a little bit more smart when it comes to writing down a good loss function, which is critical. And that's the entire reason that I'm going through these slides, is to at least maybe out of this slide, I don't require you to understand everything, but what I require is understanding the big picture. Then there is a video. In that video, we can take this pixel and then translate it into another pixel or the same pixel in another frame using an optical flow. So this is how these two images are related. First of all, in the 2D world, from one frame to the next frame, they are related according to an optical flow. If you know your optical flow, you're going to be able to warp one frame to the next frame in 2D. That's fine. The other one is depth estimation, is going to tell you how far the objects are from you. So it's going to give you a sense of the 3D. And actually here we are using it. You take a 2D pixel and then you map it into its 3D coordinates by knowing the depth. And we know that the depth is not going to give us the absolute scale. So you need to assume that you know your scale as well. Okay?
Okay.
So one of them is looking at a frame. It's making it 3D. Another one is looking at a frame, the optical flow, and taking you to the next frame. There is also another way of going to the next frame. What is that? I know this image where I can look at this scene. I know what camera I was using, or at least I can assume I know what cameras I was using. Take that pixel, go to 3D. Now you know your 3D environment. Now change the perspective of your camera to the perspective of the one from the next frame. What is going to be that pixel coordinate in this new coordinate system? What is going to be the 3D location over there?
Okay.
So one of them is about moving your camera. The other one is about the optical flow. And the other one is going from 2D to 3D. Now, all you're doing is trying to be consistent in your loss functions. If I have a 2D pixel from one frame, if I go to frame J, if I go to 3D, I want it to be consistent by me changing my coordinate system or the way that I'm rendering the scene from one frame to the next frame. So this is one mechanism, projection of one camera into the coordinate system of another camera. And then this should be consistent. So you are trying to be consistent from frame I to frame J. What else? So far, we were operating under the assumption that you know your camera, but in reality, you don't know what is your camera. You don't know what are these matrices. These are all unknown. These are the camera parameters. So you're going to do an iterative process. You assume you know your camera, estimate the depth. Assume you know the depth, estimate your camera. And then keep repeating that. But then this is not stable because the entire process depends on the exact S. And this is too strict, having a single scale for the entire scene. So you're going to relax that. You're going to say that I have multiple scales. So each pixel can have a different scale. And then the rest of it is just you going back and forth using your optical flow and the 3D coordinates to give you the final depth.
Okay.
So I want you to get the big picture. You have two frames, I and J. You can look at them in 2D and go back and forth between them using optical flow. Or you can look at them in 3D. And because now you are in 3D, you need to project. You're basically taking a camera, rotating it, translating it, and then that's going to give you another coordinate.
Okay.
So you have two ways of going back and forth between your two frames. One of them is optical flow. The other one is different coordinate systems, the way that you are filming the scene. So the pose of your camera matters. And this is exactly what we did in the previous paper as well. You had 3 images, or you can have 2 images. From one image to the next one, you're just changing the pose of your camera.
Okay.
So this T matrix that you see here is exactly these R and T small t's, the translation and rotation. One of them is happening in 3D, the other one is happening in 2D. Actually, even this one is in 3D because you're taking into account the depth.
Gotcha. Okay. Okay. Thanks. See you on Monday.
Yeah.